Alright, another draft physics video presentation. Third in a series of videos covering the four major phenomenons of nature, you could say. Magnetism, light, charge, and gravity. So we're on gravity. The conventional theory is kind of subject to interpretation. They don't really have one. They say there's something called the virtual photon. That's basically a little bit of energy somehow. And somehow it just magically decides when it hits something that it attracts rather than repels, or that it repels in the other circumstance. But there's no real mechanism, no explanation of where the energy comes from. Two magnets interact and there's just no explanation. I guess I should play this video, so I'll just play this in the background. It'll at least show some magnets doing magnetic things. But they really just don't have a mechanism, and certainly don't have an accounting of the energy, just like they don't have an accounting for the energy in gravity. Things move, and we're supposed to believe they did it because space told them to, or something told them to, and they don't have a mechanism. And starting from the beginning again, I would argue that there is a mechanism, and it's called force, and the force exists in the universe, and it comes in these two kinds. And it moves the speed of light in straight lines, and that's all it does, and it's perpetual and forever. Every little bit of force in the universe, every piece of a photon, everything you interact with, every bit of heat, has been in the universe since the universe existed, and it's been all kinds of places and done all kinds of things. It never stops doing its thing. Complementing those bits of force are matter, and that comes in the form of electrons and protons, and we'll just arbitrarily call that an electron and call this a proton. And the two bits interact inversely with the two kinds of force. So you could call this the electron force and this the electron. And the fact is they'll act completely opposite depending on what force hits them. So there's two kinds of force, there's two kinds of matter. Now, the two kinds of matter don't have any innate motion. They only move based on what the force does to them. So if I was to have an electron and it's in this field of force, the universe is just made of this force stuff all over the place, like the cosmic background radiation. It's always there, it's always moving. There's an equal amount of it, and the fact is we'll just put little heads on the arrows for the fun of it. Oh, same color. Anyway, so the force is around everything, constantly interacting, and the electron and the proton are kind of like little bubbles. They just go wherever the force hits them. So if a force hits them, you could think of it having Velcro, but the Velcro can only hold one object at a time. Or you can think of it as pool balls. And when you have two right next to each other, if you hit it with the one this way, you could sort of understand that this one will stick and this one will go. This one will leave and this one will attach. So at any one time, it only has one attached to it. So at any one time, that's all that can ever be attached to it is one. And depending on the environment, so if this one does hit it and this one flies off, and there's the next one that's going to hit it is way over here, it's going to hit this way. Well, you can see it could travel as much distance as till it hits one going the opposite way, and then it's going to go the opposite way. So it's just jerked around. The force decides where the matter goes, not space, but force. And the two interactions are a pure reflection, that is, when the same color hits, it reflects, and there is momentum in that direction until the reflection will happen when the other guy hits. So the reflection isn't happen first. So first the force goes in, and then when something hits the opposite way, then you have the reflection, of course, of the force, and you have a bit of movement until you hit the equal but opposite force, as Newton would say. So that's one interaction, and the other interaction is when the opposite force hits. So this holds also for the proton. When the opposite force hits, the interaction is switched from this dimension, the forward dimension, to one of the other two dimensions. And so it can be in and out, or it can be left and right. And what will happen is the force will leave, the reflection will leave in one direction, and the momentum will be in the other direction. And that is all you need. So 2 forces, 2 matter bits, 2 interactions. And you can explain all 4 of the fundamental phenomenon. You can unify physics and be done with all the woo. So for the magnet, I guess we'll just do the basic function first and then get into structure a little bit, I suppose. So anyway, you have a magnet. You have this force coming in from all directions that we would call gravity, you could even say. So it's like, there's gravity is made of this force, and the cosmic background radiation, light, and everything that hits something is a force. It's just there's very different amounts of it. Light is a tiny, tiny fraction of the amount of force hitting you. So anyway, the force comes in, and what happens is that all the yellow bits, are turned by so if a yellow bit hits the blue bit, it's turned. That is, the force leaves, the reflection, out the yellow end. And conversely, if a force bit hits the yellow bit, it is, a blue bit, then comes out the blue end. So obviously all the blue bits that hit reflect back. So you have all the blue reflections, right? So all the blue stuff will reflect off the blue end. And all the blue that went into the yellow will reflect out of the blue end. So then you have all blue coming out of one end. And obviously how strong the magnet is, that how much of the material is doing this filtering, will decide how much, or how powerful the magnet is at segregating the 2 forces. But that's all that basically will happen, is that the mixed force will come in and a segregated force will come out. And kind of obviously, one end, this end, and the other opposite end will have disproportionately a lot more of these arrows, because they're doing the conversion of everything that comes in the sides. So you can sort of figure out that there's going to be more force at the 2 polar ends and less at the sides, and that anything sitting at the side, any object like an electron sitting here, is going to get, both forces are going to be acting on it. So one force is going to be reflecting, pushing it away. The other force is going to be moving it sideways. And the mixture will be a tendency to move away from the end that's pushing actually away. The sideways motion doesn't mean much, and so the object will move in a direction of attraction to the north end and a repulsion from the top end. And you got to understand it's getting hit by mixed force here, so it's getting some attraction and some repulsion, and therefore, obviously, if I put the electron at this end, it's more likely to go that way. Alright, so that's the basic idea. So a magnet is just filtering, and that's where the energy comes from. So the energy comes from the external universe. It filters that energy, and that affects electrons and protons profoundly, in the sense that their field changes, and the field around them, what they're getting hit by, and if they're getting hit by a force that reflects off of them, it's going to move them away. And if they get hit by the inverse one that moves them sideways, well, that's not going to be as big an issue, because they'll move both ways and they'll just wobble in space. So that's the basic mechanism. It works. Simple dynamic, no woo involved, no virtual anythings, no waves anywhere in sight. It's all straight line force, and the straight line force does explain all the mathematics, because the mathematics really goes back to charge and goes back to the idea that all an electron can do is reflect the world that comes at it. And even if it's blue, it's a kind of reflection. It will send energy in a new direction, but it's still just a reflection. So everything emits a profile of itself. I mean, it's a signature. And so when you combine 2 of these objects, so if you take 2 atomic bits, an electron and a proton, and you do manage to put them next to each other, you essentially do have a dipole magnet in function. And the magnet is just made out of these dipoles created in atoms. So you can take this little example and turn it into a whole atom, in the sense that you could understand that an atom can have more electrons on one side just because of certain geometries, than it has on the other side, and so it has a disproportion. That is, it's more bluish this way and more yellowish. Little cat. More yellowish going this way. So you can understand it as being polar in the sense it's like a multiple dipole, but you could just understand that it would have a polarity, and the atoms line up with that polarity, and that ends up creating essentially little magnets. And once you have the atoms making little magnets, then you can pile, the magnets next to each other in a structure where you just stagger these atoms, and you understand they're connected to each other. So when they break, like a magnet will do when it breaks, they won't break the atoms, they'll break the connections between the atoms. So if I were to make a structure, I could put another one right here, and you could understand. So they'll always line up on the attractive sides and to minimize the repulsion. So they'll again create a geometry that's conducive to the function. And if I were to break this structure, so yes, this goes out, and I was going to break it, well, I'd end up breaking it on this line, right? I wouldn't break atoms, I'd break between atoms. This is an atom. And so it would break with the blues all at one end and the yellows all on the other end. So it would end up creating a north and south again. So it would just create another magnet. So you can understand the whole why magnets break into two new magnets is because they don't break atoms in half, they break between the atoms. And because of the geometry of the atoms, because you've aligned all the atoms. So again, that's something to understand, is that in the materials that are magnetic, this actually goes to bubble theory, in the sense that they did back in the 50s experiments with little bubbles, and you could make a whole field of little bubbles on the surface of water, and the little bubbles create this kind of geometry with each other, in the sense that they create a very strict geometry, and it ends up that they stick to each other in a very specific ways that has some linearity to it. And so one group will be this way, and another group will be lined up this way, and another group this way, and they'll be all in the matrix of the metal. And so these would end up being what's called domains or crystals. And so all the metals have this tendency to turn into crystals, so they end up being little blocks that slide across and around each other, and they have these borders, okay, that can cause a little bit of erraticacy, and they have to slide across each other because they're not quite lined up right. Their geometry's a little off, and you can see that in crystal, in metals when you polish them. You can see the crystals, especially aluminum. And so that's the nature of the material. And the idea would be is that when you magnetize, when you expose a material like that to a specific field, that all of these little bits in these domains will tend to want to turn all of their geometries in the same direction. So they'll start to align. And when they do that alignment, then they just emphasize this function where, I could just put little arrows on all these little yellow lines and just get the idea that all the yellow energy will go one way and all the blue energy will end up going the other way. And it will become a magnet. It'll filter just like this does because everything will be aligned in the same geometry. They won't be defeating each other's purpose. When the crystals aren't in the same orientation, then one's producing blue going this way and another one's producing it going this way and another one's doing it. So you can see it just ends up being mixed, and you end up not having any change in the field coming out. It ends up being the same field of a randomized field, and so it's non-magnetic. But as soon as you cause that alignment to take place, then you'll end up with all yellow coming out of one side, or more yellow. I mean, again, it's just a more argument, and then it would be all blue coming out of the other side, and you end up with a magnet. Alright, so it's really just understand these as blocks, as atoms, and the atoms are really just made out of the electrons and protons, so you can understand it's just another level higher to get to domains, because they end up being polarized, and so everything just ends up being another copy of the same kind of basic function of just arranging charges in a place where the repelling the key to understanding. I didn't do the repulsion part because I did that in the other, but you can understand that like objects would end up trapping force between them, and the force would magnify with proximity. So the closer they get, the more energy they're creating, because the same little bit of energy bounces much faster and has more interactions. And interactions decide energy, essentially. Energy is interactions. So it's hitting. You have to hit something. And it's always, because they're always moving the same speed, the constant speed of light, they always impose the same amount of push. So no matter, it doesn't matter how many times they hit, they don't slow down, they don't get weaker. So each hit imposes momentum. So momentum goes up as proximity increases. So the closer they get, the higher their potential to move. The higher the pressure. You could just understand it as just being pressure. So anyway, so obviously all these bits want to maximize their distance. All the blues want to be as far away from the other blues, and all the yellows want to be as far away from the other yellows. And clearly you can have arrangements, where you have two yellows and you put a blue in between them, and the implication is that you can have two yellows very close to each other, because all the yellow energy will perpendicularly leave through the blue object, and now you won't have any reflections between the two yellow objects, because you've negated all of them with the opposite charge. And that explains why the nucleuses are dense and why atoms can be as small as they are, considering the amount of repulsion that exists between the individual players. All right, now the forms of magnetism. There's all the iron-based and cobalt and nickel. There's a few little elements, 3 or 4 of them, they already have atoms that are polar. So the atom already has a bias, in the sense that it, as stated, it's, I would argue the bias is this. Okay, I mean, 2 sides are north and 2 sides are positive, and that's the same difference as polarity in another respect, and it really just has to do with the distance of the electrons moving in their shells, the atom expanding or contracting, the atom distorting in its shape. So when the atom's in its normal condition, it's neutral, but if you compress it, you stretch it, well, then it's going to tend to go polar, in the sense that the electrons will end up moving away, further away, and you'll end up with more protons being exposed on the 2 sides. So the atom becomes a polar atom. So in magnetism, what's basically happening is these are the alignments of the atom. This is its north, and this is its south pole, you could say, or dimension, and they're just moving to line up with the magnetic field. So there's a magnetic field hitting it, and mostly, let's say yellow from this side and blue from this side. You could understand that the yellow bits are going to want to align with the yellow, and the blue is going to want to align with the blue, and so it's going to turn to maximize its exposure. So it'll maximize its it'll want to have as much blue facing the yellow as possible, because that's like a vacuum to it, and it'll want to have as much yellow facing the blue, so the blue force. So you can understand that it'll take this atom and turn it, this way, so it can be as comfortable as possible. That is, the least amount of repulsion and the most amount of attraction. Just maximize that circumstance. So a piece of iron or whatever has atoms that can rotate, and the rotation means they can all start aligning, and that they'll all end up becoming a magnet themselves. And so you can understand why just exposing a piece of iron to a magnetic field magnetizes it, because you put it in a field that's going to rotate its atoms, and those atoms now are going to be in alignment geometrically that's going to make them a magnet also. Now, paramagnetism is when you have that, you have a magnetic material, And what happens is it's basically the surface has electrons are on the outside of the atoms. You can understand that. And what you're going to do is now you're going to move a magnet into that surface. And the key is that you're going to move it, which means you're going to be increasing the amount of magnetism, right? I mean, the closer you get, the more reflections off those electrons, creating increased pressure. So all the yellow force is going to start bouncing back and forth with the yellow end of the magnet. So if I go in with the yellow end of the magnet, so here's the north end. I go in with the north end and I'm flying towards this material. Well, it's going to want to move those electrons because I'm hitting it with a lot of electron force, and because this is the north end, so this is all yellow stuff coming out of here. And the trick is it's going to move all of them at once, and it's going to move them faster than they can turn, where the electrons can move to the back and the protons can move to the front. So because the material is going to be made out of atoms that are staggered, that is, the blue bits are as far away from each other as they can be, and the red and yellow bits are as far away from them, it's going to tend to want to, convert charge. It's going to charge, but it can't because it doesn't have time. So you're pushing the force in so fast that all you end up doing is taking electrons that were on a surface with a certain distance from each other, okay, because they're all connected to protons, right? So you can sort of understand that if I put 3 nucleuses there, that if I push on these electrons, what's going to happen is they're going to tend to get closer together. So they're going to end up, the closer they get to the atoms, the surface, they move towards each other, which causes them more pressure. So they end up filling the space. So if it's sort of like an image, you can understand that if I put a barrier up of soldiers and they're this far apart, well, then lots of stuff can miss. But as I move them closer to the castle, all right, they end up being closer to each other. And when they're closer to each other, more of the forces are going to hit each soldier. And so there's going to be more reflections, and that means more energy. And so it compounds the energy. So the magnet moving in pushes on the force. The electrons end up compressing, filling in all the gaps. And by filling in the gaps, they're essentially becoming a north face charge. And that north face charge is just going to sit there and repel what's taking place. So this will essentially become an opposite magnet. But it's only a temporary condition. It only exists while you're pushing, because the electrons will find balance if they're given enough time. So if you quit moving the magnet, the electrons will separate from each other by creating new patterns in the atom, and will create the normal amount of gaps, and everything will go back to normal again. So it's just that the electrons don't have time to move. That is, move in a staggered way. See, the idea is there's a door open, and the idea is when you put one electron at a time through the door, everything's okay. But if you try to cram 5 or 6 electrons at the same time through the door, none of them can get through the door. That's sort of the way to look at it. There's little gaps in the material between the atoms where it's okay to rotate into those gaps. But the atoms can't rotate between those gaps when too many are trying to get through the door at the same time, or trying to rotate at the same time. They all can't rotate at the same time. And if they do, they end up being a block here, and it becomes a magnet for a little millisecond, until we can push one at a time through. So essentially that's all. It's a temporary magnetic effect by just compressing electrons, and so it temporarily becomes an opposing magnet. So it doesn't have complementary magnetism. So where the iron creates complementary magnetism, that is, the magnet is oriented, say, this way, the piece of iron, okay, the iron filing, will line up complementary to that arrangement, in the sense that it will do the opposite arrangement. So it'll do the maximize the attraction and minimize the repulsion. And so it will flip or turn or to be in this complementary position where, so that's ferromagnetism does that, and the paramagnetism does the opposite. It creates magnets that are in the same configuration, and so they are repulsive because they're lined up the same. So paramagnetism creates an opposing force. Ferromagnetism creates a complementary relationship. It doesn't change the force, it just changes how the two things can interact. Obviously, this blue thing is going to have all its energy just come out of the yellow thing. The yellow energy will come out of the blue, so you have a vacuum between where you have repulsion here, where you end up with have a lot of the bits just bouncing back and forth, and likewise the bits here will bounce back and forth, the blue and the yellow, and so you have repulsion. All right, so I don't know. I guess we'll take a pause there and see. Maybe I'll connect it to electricity now, but I'll think about that for a second. All right, should be back. I think we will do the line of force argument again, just to it's similar to charge, just to understand that what they draw as a magnet is how they describe the significant features of a magnet is a bit off. And this is sort of Faraday's problem. I mean, Faraday's mistake that we're just living with forever. But the idea is, so I'm pointing out, the magnet has force that's reflecting off of it. It's reflecting whatever the universe is about it, and it's all the yellow that went in this way is going out this way. So obviously there's more yellows, and well, anyway, segregating the two forces. So more blue this end, more yellow the other end, and it's just a force. And it has, with distance, you can understand, just like a light bulb, with distance it's going to degrade. Now, unlike a light bulb, it's two colors at the same time. So the degrade is going to be more substantial, because you can sort of understand that any object at this distance is getting hit by both forces. And so it's going to get some pull and some push, so to speak. It's going to create a vacuum, but it's also going to create some reflections. So it ends up being an R-cubed rule for magnetism. But anyway, in the mixed side. It doesn't happen at the polar side. It's still R squared there. So basically the magnet's producing this field. Now if I put another magnet in the field, and all I have to do is throw a piece of iron in, it automatically magnetize. So if I have little pieces of iron, they're going to line up with the magnetic field. That is, they're going to line up with their complementary. So they minimize the repulsion and maximize the attraction, so they line up in the same orientation as the magnet is in. Draw another one just so you get the idea. And the truth is that all the iron filings are going to line up that same way. And so what they're going to do is they're going to be repelling each other, because the ones next to each other, they're both being magnetized by the same thing. See, everything's being magnetized by the same thing. It's in the same magnetic field. And so the same would be true for compass needles. Compass needles and iron filings are going to be the same thing. These are going to magnetize, except the compass needle can't change its magnetism. So you can test the field by moving a compass needle around and see where it's complementary, but it's an arbitrary test in a sense. That, yeah, of course, the compass needle will turn to always be complementary. But the iron filings are doing the same thing, and what's happening with them is they're sort of showing you the problem here is that this one magnet induces the magnetism in all these other little magnets. But obviously they're going to be repelling each other because they're lined up they're being magnetized by one magnet complementary to this one. They're not complementary to each other. So what they're going to do is force distance between each other. So the next one's going to be over here, and then a few of them will pile up complementary to each other. That is, they'll stagger their magnetism. So another one will connect to this one with its heads and tails, in the proper order. Head connected to tail, connected to head, connected to tail, And so that's why there's lines between, when you see the regular field lines, that's why they could do this thing. Okay, it's because when you spread the iron filings, what they're doing is creating new magnets, and essentially the opposite configuration, right? South north, and all of the new magnets repel each other. So this one repels this one, repels this one, repels this one. Is attracted to that one. So it's just a matter of all these repel each other, and that creates the spacing between them. You can sort of get that idea. So these lines are completely arbitrary. They're dependent on how much material you throw down, how fast you throw it down. These lines will be in all kinds of different places, depending on what you're using to see it, the phenomenon. But they're not real. There's nothing flowing through the magnet around here. They'll put arrows on it because it has some significance to how it induces electricity. One end is the electron end, one end is the proton end, so to speak. So in truth, they will create an inverse effect. All right, should be back. Better check to make sure. I don't want to waste too much time. Anyway, so where was I? Okay, so what Faraday did was basically make the mistake of, these are what should have been called lines of force. And he ends up kind of calling these lines of force, these field lines, end up being called the line of force. And he started trying to think of how these things travel and manipulate things. And these aren't really lines of anything. These are just representations of where things will line up. But there's no motion here ever detected. Nothing's actually moving around the magnet. The magnet's radiating like a light bulb. So you could think of it as a light bulb where one side radiates blue and one side radiates red. And it'll exactly work out with Maxwell's equations if you think of it that way. And at a distance it's going to look purple. From this side it will look purple. From this side it'll look blue. From this side it'll look red. From this side it'll look purple. And depending on how the magnet's configured, it's going to change that color, and it works out perfectly fine. And so you'd understand that this magnet is, red is coming out, and then the field lines would be shining blue out this way, So you could understand that that's all that's changed is the orientation of the light bulbs, which side is blue and which side is red. And if you just follow it like that, thinking about it as photons flying out of these things that are a different color, you can see magnetism much clearer. You can understand it better. All right, so I think that's all we need for that. So the next step would be kind of understanding the atom part of it in electricity. So I would argue that the atoms are arranged in a substance, probably in arrangements that are more like this, okay, where they're sort of canted to each other, connecting each other. And the idea is that electricity comes into this crystal of bubbles, this arrangement, and you can think of it as it runs across these patterns here, the outside edges of bubbles. You can think of it happening lots of ways, but the real important feature is just to understand that what's probably happening is that this is a compression. This is an electron force, so it's pushing on electrons. The electron pushes in, which causes the other electrons to push out. So you can sort of understand that the atoms are basically just polarizing. So when electricity or force comes in, the electron force, it's pushing the electrons, which is making these things blue. These two sides become blue and these two sides become yellow. So they start off, let's say, white. Could have drawn it that way, I suppose, neutral. And they end up getting polarized. So all you're really doing is just changing the shape of the atom. You're giving it a polarization. And in doing that, you're temporarily magnetizing it. So that's the connection between electricity and magnetism. So if I connect, see, electricity is basically two points to it. It's how fast you change something as voltage. So how much pressure I push in one time, and it goes through one series of atoms. So I could have one series of atoms and put a lot of pressure, move them very fast through just one string of atoms, and end up with 1,000 watts, right? Or I can take a low pressure, a small amount of force, and go through a lot of atoms. Okay, so I'm taking a little bit of pressure, but I'm going through a lot of atoms, and I can have 1,000 watts. So I can get my 1,000 watts, my amount of push, through either mechanism, either through a high voltage, but very few atoms are involved, or with a high amperage and lots of atoms are involved. And the trick is with magnetism, if you want to create it in a wire, you have to do the volume thing. So that makes sense, right? You have to affect a lot. You have to convert a lot of atoms into polar atoms to be able to turn it into a magnet. It's not much substance, right? The wire isn't, a tremendous amount of matter, and you're going to try to magnetize it. Well, you can't magnetize it if you send a high pressure through. You're only magnetizing a tiny percentage of the atoms, because the high pressure only needs a few atoms to be involved in the transmission. But a low pressure, okay, low voltage, affecting, that is, lots of area of rays, lots of areas of pressure. I don't know how to say that exactly, but lots of electrons versus one electron going very fast. So you have the choice of lots of electrons going 20 miles an hour or one electron going 70 miles an hour. And it's just that kind of conversion. So you need this kind of energy to create magnetism in a wire, because you need to affect a lot of atoms. So that's what you're after. Affect a lot of atoms, polarize a lot of atoms, then you can magnetize, create a north-south effect in the wire. So that's how electricity induces magnetism, is by converting as many of the elements into a magnet as possible. Now it's a plain wire. I can do another trick where I can take the wire, and if I coil it, if I take the wire and I coil it, alright, that means the wire, is in here and going around. There's two pieces to the wire, two sides. But anyway, you can sort of understand that I've created a hollow cylinder, essentially, right, that has an inside. Okay, I guess I don't know how to draw that. I do know how to draw it, but I just didn't do a very good job of drawing it. So we just dotted line this. So you can understand you could go inside the coil of wire. I guess that's the way I should have drawn it. Alright. And so you go inside the coil of wire. You can understand that inside the coil there's going to be this capacity for the reflection to take place. One side of the wire will be here, the other side is here. And the wire's been polarized by being electrified. And now the force will be reflecting inside the coil, going back and forth, back and forth. And so it's intensifying the energy by capturing it and causing these reflections. And so the electricity is creating more magnetic effect by exposing more and more atoms to the condition that's going to magnetize them. And if I put a piece of iron in there, I'll even more magnify the effect, because the iron will do the same thing in terms of becoming magnetic. So the electricity will magnetize the iron, which will in turn magnetize the wire. And so now all the energy that goes in, the electricity, ends up being converted into this energy inside the coil. And that can make the iron into a big magnet, and a stronger and stronger magnet. The more electricity I put in, the more I magnetize the iron I put inside. And so that's another way of converting the electricity, the pressure that's converting the atoms. You're misshaping polarizing the atoms, and all you're really trying to do is polarize as many atoms as possible. I'm just using triangles as a way of understanding that it's a polarized atom now. It's been pushed and distorted in its shape. And by distorting the shape of the atoms, the more atoms you misshapen, the more of a tendency to create this idea of filters. The more filters you're making, and the more filters you make, the more the whole thing becomes a big giant filter. And so you end up magnetizing it and such. Wire. Anyway, So I think that might be enough. I'll think and see if there's any other subject I need to touch upon. Alright, just thought of the problem with why magnets don't work in charge environments. So I just thought I would cover that quickly again, just to point out the reason why the expectation that a magnet and charged objects would get along. So if I have a piece of metal that's charged positive, I don't get a magnetic effect. The magnet doesn't repel the charge. It doesn't push the charge away. The magnet isn't repelled. When you say if it should be, right? What's the problem? Well, the the problem is that the charge is basically charging the metal of the atoms in the magnet. So the magnet has a function, but the function is completely dependent on all of its little magnets inside. And what's going to happen to the little magnets inside is they're going to be moved by the charge. And so they're going to end up moving because of the charge. The atoms are going to turn, and that's going to end up destroying the filter. The magnetic filter is going to be broken by the fact that it's going to want to not be positively charged. It's going to want to convert the metal atoms, and so it's going to be taking some of the atoms and forcing the electrons in, and by pushing the electrons in the opposite direction, it's flipping the proton ends, and so it's going to end up becoming, as they always do, oppositely charged on its metal surface. And the metal surface is essentially going to clog the filter, because now it's going to, where the stuff was coming out before, it's now going to reflect inside, and so you're going to be breaking the magnetic filter by breaking the fact that it was sending force out one way. So by charging a magnet, it's essentially, if you thought of it as a filter, you know, some sort of porous filter with a bunch of holes in it that let certain things through, the charge is basically just breaking the filter. It just kills the little filter holes, and now the magnet isn't going to work as a magnet anymore. It's just going to become a piece of steel, and because the exterior has been clogged, essentially. The interior is still working, but the exterior is broken, and so nothing can get, the filter's just broken by the fact that you've charged the metal of the surface. The electrons on the surface are blocking what's actually happening to the atomic structure. So the magnets exist as the atoms, but the free electrons, the electrons on the surface, are the ones now going to be converted. And by converting them, by pushing them back, you're going to basically just block the surface of the magnet by creating essentially another surface. It's almost as if you create another surface. The electrons will bounce, reflect the stuff that was supposed to be coming out of that end. And the inverse happens on the other side. Obviously, just moves them in the opposite way. So by charging a magnet, you break a magnet. It loses its magnetic function because it's essentially clogging the filter. All right, so just to explain why there's that difference in motion. Now, the other thing that happens is the motor force, which is when you put a magnet in a magnetic field. That is, you take a north side and you take a south side, and you put a wire in here, and then you run, I guess I should put the wire as a neutral color. That's probably not necessary, but you get the idea. And you put a current through the wire. Okay, so there's a current going through the wire, and it doesn't matter what direction, you'll just get an opposite effect. And the wire, instead of moving towards the north or towards the south when you're running a current through it, it either flies out, or if I switch those two magnets, it flies down. And so it's converting the dimension again. So instead of it affecting it in the way you would think, attraction or propulsion, it basically repels from one side, attracts from the other side, and, well, or both. It's left turning, so it's turning the same way from both forces. So the effect of the south end makes a right turn, you could say, and from the north end it's a left turn, but because they're opposite sides, they end up being the same thing. So it sort of breaks down the opposite effect they have because they're in opposite orientations. So by, they're opposite things, and then they're opposite sides. So it's two opposites equal a same. So that the opposite effect that they're going to have, that is the conversion this way, is, the turn it would have taken. If I put the north on that side, well, then the turn's this way. And the same thing is true for the south. So I've inverted the south this way, the turn would be that way, and the other one would be that way. And so you've just inverted the switch, and so now it's going into the other dimension. So when an electron has motion, it has a bias to reflect something perpendicular. Okay, if something's coming in perpendicular, it has a bias to send the force out this side and the momentum in the same direction as it's moving. But when that's happening in a magnetic field, it just ends up meaning it takes it out the other dimension, the other third dimension. So it either comes in or out instead of going left or right. And so they both end up going out. And so one configuration goes one way, one goes the other way. And just has to do with the fact that it's the motion of the electricity is dictating that it can't do what it normally does. So it goes to that third dimension. So as I pointed out, in the 3 dimensions, you have your choice, if you're coming into the 3 dimensions, that taking a left turn is the same as taking an upturn, outside of gravitational influences. And so any one of those 4 directions are just as easily taken. And in this circumstance, it just means that instead of going plus and minus this way, the force and the reflection move up and down because it's left and right and opposites. So it's, the thing to understand is this would have a certain when you have a north end and a north end, but you could understand that this one's pointed this way, so right would be one way. When it's pointed this way, right's the opposite way. But you can understand, but if I just invert that is, I put the south pole in the position, then it's going to invert that, and then they'll both be conducive in the same direction. So you're just taking advantage of the yin-yang, and by putting the 2 yangs on one side and 2 yangs on the other side, they both point in the same direction, however you want to look at it. Alright, so that's probably enough of a video. It covers most of the facts of magnetism. So it's, again, just made of this elemental function. All you need is momentum in the universe. You need objects that are affected by their momentum in 2 different ways, through 2 different interactions. And you explain all the things that move in the universe. Any repulsion or attraction is explained by that mechanism, and you don't need all the woo of 400 fields and all kinds of waves and all the rest of it. It's all straight line force. It's all radiation, like a light bulb or like a piece of radium. It's all radiating momentum that moves in straight lines until it's obliged to move in some other shape of line, until there's enough force to force a curve. In cases like gravity. And so that will be the next subject to conclude this series of videos. So thank you for your attention, and until the next time.